Hi, I'm Dr. T and welcome to my office. Today I'd like to talk a little bit about how we structure and organize chemistry. Chemistry, like any other field of study, is our attempt to understand nature. Nature doesn't have subdivisions. There is no subdivision between what we call physics and what we call chemistry, and what we call chemistry and what we call biology. You have things that are alive and you have the chemicals that make them up. Where one starts and the other stops is kind of a fuzzy line. Because nature doesn't have lines. But as humans, we like lines, and so we're going to put down some lines. And with chemistry, once again, we're studying things that are made up of atoms and molecules and the building blocks of stuff. But of course, there's a couple different ways you can study the building blocks of stuff. And hey, we always like more lines. So traditionally, there have been four major branches of chemistry. One of the earliest was physical chemistry. Physical chemistry is kind of that border between chemistry and physics. Understanding how atoms and molecules behave at a physical level, how they interact with light, how gases behave, and now, in the late 20th and early 21st century, how quantum physics relates to chemistry. What do electrons do? Other early fields, or the other traditional fields, include analytical chemistry. This is understanding the qualitative and quantitative nature of what you have. What do you have? What is it made of? And how much do you have? What composition do you have? What blend do you have? How much of each component is there? This, of course, parlays quite nicely into forensics, which is its own discipline. It's not chemistry, it's forensics, and as chemists we will help with that. Although it is definitely its own separate area, as well as things like metallurgy, assessing what kind of rock do I have, how much gold do I have here, etc. So a useful field, quite often doing a lot with environmental and a lot with other fields. The next two branches are an interesting set. Historically, it was believed, once again, 19th century or so, that living things were special and they had a vital force in them, and that molecules that came from living things were different than molecules that came from inanimate objects. So you could have, say, sodium nitrate, which comes from rocks, and that was inorganic, it was an inanimate object. And you could have something like urea, which is, if you remember, what number one into the toilet is for, what your kidneys take out. And that would be an organic molecule. Then that definition stuck for a little while, but then all of a sudden we realized that, whoops, that vital force thing, yeah, maybe not a thing, and we needed to redefine our definition. The impetus for this was a rather interesting inadvertent discovery. A researcher had mixed several reagents together and put them on a shelf because, he got busy. And there were crystals that had formed. A chemical reaction had taken place, and the crystals were very characteristic of urea. And all subsequent tests said that this was urea. Urea had been produced. An organic molecule was created from inorganic molecules. Oh boy. There was a problem. That shouldn't have been able to happen. But of course, there is no vital force. Molecules are molecules, and you can arrange them. And sometimes you can arrange things that come from rocks into things that come from, people and dogs, or, as was said, urea synthesized without the help of man nor dog. So the definitions had to change. Organic chemistry became the chemistry of carbon, as well as some of its common atoms. And inorganic chemistry was the chemistry of everything else. Traditionally the chemistry of metals, but not exclusively. Now, the definitions, by the way, are a little bit fuzzy. Things like diamonds are not considered organic, even though they're pure carbon. But chemistry of carbon is a good working definition of organic. Now, as time progressed, we did come back to the revelation that we did need a chemistry of life, although there was no vital forces, so we had to redefine how it was. And in the 1970s was created biochemistry. Biochemistry is the study of biological molecules. Now, some of those molecules are exactly the same molecule as come in non-biological sources, and we're totally okay with that because, you know what, things blend over. So our fifth major branch of chemistry. Now, there are other fairly notable branches, and depending on who you ask, depends on how many we have. Chem Ed is a growing branch that's chemistry blended with psychology to study the way people learn chemistry. And all these branches have a myriad of sub-disciplines within each of those, and there's lots of crossovers. There are individuals who are biophysical inorganic chemists, which basically means they're most of everything at once. And that's normal because remember, we're studying nature. We're studying something that doesn't have nice discrete lines, and that's to be expected. And of course, as chemists, we are the central science. We are the foundation for a lot of other disciplines, and of course we've got crossovers. Biochemistry is obviously a crossover with biology, and I was cross-trained with the biology students at my school. Geochemistry, of course, is crossing over with geology. And really, any two fields, you can probably find someone who's doing both at the same time and sticking a hyphen in between it. With that said, see you next time.